Do you face problem while working with your data science project that you are not getting the desired results even after applying the right algorithm and the right parameters within the algorithm? Well, this is an everyday task or an everyday scenario of a data scientist that you are not getting the desired results even after applying the right algorithm. Well, in this video, I will show you a couple of data transformation techniques that you can apply to your algorithms before supplying the data to the algorithm and see whether this is making any difference. As part of any data science job, it is a duty of a data scientist to keep on experimenting with the data and with the algorithm until you get the desired or the accepted results. And these data transformation techniques, which I will be teaching you in this video, is part of that experiment, because some algorithms take the transformed data uh, or accept the transformed data in much better way than the normal or the original data. So these data transformation techniques that I will show you will going to help you to experiment with your data and get the desired results from your project or from your data science project that you are having in hand. So let's go ahead and get started. All right, so here we are for the project 2. Project 1 is something which I uploaded it earlier. So that is present in the same notebook. I am keeping it in the same notebook so that you don't have to request the access, as well as follow a new link altogether. And for me also to maintain entire code in just one workbook is quite easy, and similar is the case for you. So what I'll do is I will paste the link of this notebook into the description, and you can download it from there in case you want to use it for your reference, as well as the dataset link. So if you already have the dataset access, then you don't have to request it again. So let's go ahead and get started. First of all, importing the libraries, because we are starting with absolutely new kernel. So importing pandas as pd and import matplotlib.pyplot as plt and percentage matplotlib inline. Just basic libraries for data access, data manipulation, data visualization, and for printing the plots within the line itself or after the cell. All right. First task is getting the data. So to get the data, I'll just go up very quickly, copy this because this is what I want, and I will go down, come here, paste it. What we are saying is we are creating this object, reading the file read.csv, daily total female birth in California. We want first column to be indexed, which is dates, and we want to parse the date so that Python can know once the data within this object that first column contains date. So 0 indicates the index number or the column number which starts from 0. 0 indicates first column, 1 indicates second column. So indexing starts from 0 within Python, if you are not aware. So if you execute this, the quick check like we did earlier. Oops, I do this mistake all the time, but I hope you can leave it. So this is the data that we got. This is the first column, index column. This is the number, female birth in California every day. So 1st January 1959, 35 birth. On 2nd January, 32 girl child born. On 3rd, 30, and on 4th, and so on and so forth. All right. One issue we saw earlier with this data, if I say tail, is having this line into your data set, which is nothing but indicating that this is a file name and this is the year. We have to remove this because this can create problems, and to do that, birth equals to f underscore birth from 0 to 365. So if you see, This is a 365 data 365 data set because it is starting from 1959 January 01 going until 1959 December 31st, and this is the row. And as you know, the indexing start from 0, so this is basically 0 going up till this is 364 and this is 365. But in our index we are taking 0 to 365. Why is that? So that's maybe an interview question, that why you are picking up even the last row into the data set, and what it will do. Well, as per Python documentation, the last row or the last index number that you specify is exclusive, it doesn't count, and because of that it will not going to pick this particular row, which is the 365 row, because row is starting from 0 to 364 because it is a 365 data set, and since it includes 0 it becomes 365, and this is 366, but index number is 365, so we need to remove that. If I do that and now see the tail part, we should not have this, right? So I hope now you are clear why we are doing it. The last number is exclusive within the Python in this index, it does not count it. All right, so now let's go ahead and do the data transformation. To do the data transformation, the very first technique that we have is normalization. So normalization is basically useful in two cases. One is, I'll just put it so that you can refer it later as part of the notes of this series. One is if your data is on different scales, right? For example, you are getting the data for the different heights of individuals, probably let's say female in this case. So what may happen is there are some people who may be capturing the height within the centimeters. There may be people who may be capturing it in the meters. So if your data is on different scales, it will be a different value altogether. So you may want to bring every data point on the same scale. Another way or another reason why you would like to do that is there are some algorithms like linear regression, logistic regression, and couple of more that basically works well when your data is normalized. When we say normalized, that means it is not having the high fluctuation, that means high low points and high down points, and it is normalized in a way that it represents a proper consistent structure. And when we do the normalization, the data will always be within the range of 0 and 1, and you will see it how in couple of minutes. Well, because some algorithms work better when data is normalized. Third reason, I would just, as part of fun, I would say because you are data scientist and you have to keep on exploring with data transformation techniques. All right, I think that is sufficient enough reason to normalize our data as part of the data transformation. So the formula for normalization is, so let's say normalization equals to x minus minimum divided by maximum minus minimum. So this is our formula for normalization. You can create even your own function, but the scikit-learn has the method for doing the normalization without you even creating any formula. So what it does is basically it picks up the value that you are giving. So the dataset value like 37, 52, 48, this is nothing but the x value. But from this data set, there will be one minimum value and one maximum value. So for example, f underscore birth dot min. So minimum value is 23. That means at least, or on a particular given day, 23 female birth child happen, and that is the lowest on a given day within the period of 365 days. Similarly, f underscore birth dot max, so that indicates that you had 73 as the maximum number of female birth child happened on a given day within the period of 1 January 1959 to 31st December 1959. So now you know x, now you know min, right? Max, min, and x, all of these things you know. So let's try to fit the 37 and see what output we get. So that will be, in this case, in a bracket, 37 minus minimum, which is 23, divided by 73 minus 23. And if we execute this, it will be 0.28. So your value 37 is transformed from 37 to 0.28. As I mentioned, that it will always be within the range of 0 and 1. Similarly, we can take example of 55, and what happens is 55 minus 23 divided by 73 minus 23, and it is 0.64, right? So as you can see, the algorithm, when it picks, there is a large variation when it comes to 37 and 55 as it compares to 28 and 64. So all of your value within a one good range, which can remove a lot of ups and highs and downs of the data set, and may try to give you the better results. So this is what it will going to happen in the back end when you will apply this algorithm. So let's go ahead and see how we can apply this algorithm. So from sklearn.preprocessing, import min max scalar. I just pressed tab and it has given me the output. So min max scalars works on an array of data. So what do we need is basically create an array birth underscore ARR, and it is simple. If you have followed my video yesterday, it is simply like f underscore birth dot values. So if I say birth underscore ARR, this is how the columns or the data looks like. All right, so now let's go ahead and specify scalar equals to min max scalar, and we need to specify the feature range, which indicate basically how many features you want to take into consideration when you are transforming it. So in this case, we only have 0 and 1, just the date and the number of arrays. So we'll go ahead and execute this. So now we will go ahead and fit it. Scalar dot fit values. All right, something else, birth underscore ARR, is that what we have specified? Birth underscore ARR, and now we have the values within this object. So to identify what are those values, we can say scalar, or maybe here itself, scalar dot data min. So it has identified what is the minimum value. Similarly, data underscore max is this. There is another one, range 50. So even if we see data, there are like a lot of different methods. So the next method we will going to apply is the fit underscore transform, and the not fit transform but the transform. So scalar dot transform, or maybe what I'll do is I'll just keep this just so that you can refer it later when you will see this. So birth underscore normalize equals to scalar dot transform and the array. So now the transformed value data transformation is completed, and the transform value are present inside the birth underscore normalize. So if you want to see the value birth underscore normalize 0, this is what the value is, 0.24 for the 35, right? And birth underscore normalize 1, right? This. And similarly, if you want to print more, you can mention a for loop for I in, let's say, 5 values. 5 print birth underscore normalize I, and execute this, and you will get the first 5 values. Okay, so this way you can print the transformed values. Now this data, once we are done with the normalization, it is ready to pick or ready to be inserted into the algorithm. So algorithm we earlier mentioned was the ARIMA algorithm. So if I go up a little bit here, yeah, from statsmodel.tsa, so this and this, there are these 2 import statements that we need to do from the first model. So statmodels.tsa.arima model, and then specify the ARIMA model. And before that, it will be good to train and test the data. So Control A, Control C, I will just copy and paste so that I don't have to create it. So f birth over here, and what I need to do in this case is I need to mention the birth underscore normalize, right? Because we want to take the normalized value. Execute. This is how the system is. So birth underscore train dot size, birth underscore test dot size, 330 plus 35 is 365. So we have entire data. Okay, and now I will go ahead and from stats models.tsa, and I think it was the, if I am not wrong, the ARIMA model. Yeah, just wanted to confirm that. Dot ARIMA model, import ARIMA. Okay, and then afterwards we need to create a model first of all. Then birth underscore model equals to ARIMA, and within that you have birth underscore train comma order equals to, if I'm not wrong, this was 212. I can check. Yeah, 213. So I think 213 is something what we can take, and then we can compare with the AIC value. So in the last video I mentioned, the lesser the value of AIC, the better the model is. So birth model underscore fit is the next command, and then the AIC what we need. So if you go down and execute this, birth underscore model underscore fit equals to birth underscore model dot fit, and birth, right now I'll just ignore this warning, birth underscore model dot fit dot AIC. So it has gone down a lot. If you see, it has gone into a negative minus 344. So earlier we had the AIC, if I go up, it was 2230, but after doing the transformation of the value, we got a new value which is in negative. So we need to really see how the predictions are coming once we are applying this. So this is also going in a complete different direction, but we still need to see how the forecast is coming. And to do the forecast, I have already mentioned in the previous video, this is how your value should be. So I'll just copy this piece and come over here. So birth underscore forecast is birth underscore model underscore fit. So our object is same, and dot forecast steps is 35, because the test size is 35. So we can identify the mean squared error in that case. So we execute this, and birth underscore forecast is this, and birth underscore test is this. So you'll see that these values are very consistent. This is like 46.46, 0.46, some variation after the when the third decimal point start, and over here it is a bit of a variation, like you can find 0.2, 0.4. So having a cursory look gives us the idea that probably the normalization is not giving the good result, but we can always do the testing. So import sklearn dot metrics from import mean squared error and import numpy as np, because I need to use the np.sqrt method to take a square root. And what I can do is mean squared error within that. So birth underscore test, birth underscore forecast 0.02, and I will take sqrt of this np dot 0.14. so this is our error rate, 0.14, very less error as compared to what we got it over here. If I have it 6.8, right? But what we need to do is to calculate it properly, we need to take both of these values into their proper actual values. So what I'll do is birth underscore forecast underscore reverse equals to birth underscore forecast, and no, I need is scalar. With that it will not come, the inverse sc scalar dot inverse underscore transform, and birth underscore forecast. Alright, value error, reshape your data either using -1. Okay, so reshaping of the data is required. So to birth underscore forecast underscore, let's create a new object so that we are not changing the object itself. So that will be birth underscore forecast dot reshape. So length of our birth forecast value, birth underscore forecast, and as per the order which is needed over here. Okay, and I will just cut it for a moment. So the values are reshaped, and birth underscore reverse, I'll just correct that, just the spelling was incorrect. So birth underscore forecast underscore reshape, I hope it should work now. Yeah, it has worked now. So birth underscore forecast underscore reverse, so these are the reverse value, as you can see, for the forecasted output, right? And this is the similar technique we can apply on the test data. So birth underscore test underscore reverse equals to birth, so birth forecast, and here we need to take birth underscore test dot reshape. First we need to reshape length of birth underscore test comma 1, keeping in the order which it needs, birth underscore test underscore reverse equals to scalar dot reverse inverse transform, and then the birth underscore test reshape. And now I can take the mean squared error. Within that, birth underscore test underscore reverse birth underscore forecast reverse, and that is that our error rate is 7.2. So that is what I just wanted to show you, that you cannot compare this value to the value above, because this is the output after we did the transformation, and this is the output, or the previous output which I showed above, that was somewhere around 6 point something. If I go up, where is it, 6.8, right? And here it is 7.23. So definitely this transformation technique has not paid off, and you will not go ahead and use it. So this way you can see that how we can basically do the entire transformation of the data using the data normalization technique, and then compare the result, that whether this transformation technique is really paying off the result within this algorithm, which is ARIMA, or the time series forecasting, or not. Another method that we can employ is the standardization, which is much more advanced as compared to the normalization, because what it takes is basically the mean and standard deviation into the consideration, and then apply the standardization on the data. So the formula is somehow similar, that is x minus mean divided by ST, which is standard deviation. So what you need to know is basically the mean and the standard deviation. So NumPy has the features like np dot mean or np dot standard deviation. I think that is present. I just need to figure it out the right syntax, like we did in the case of min and max. But sklearn has the standard metric for the standardization. So standardization is much more robust when it comes to standardizing the data as compared to the normalization. And normalization basically expect that you are doing everything within the range, that means within the min and max. However, out of range, if you are going, or your data is going bit of an out of range, like for example, if you have a trending up or trending down data, which will have the range always either going up or going down, that means it will be outside of the range of minimum and maximum most of the time, you can apply the standardization technique. So I'll just go ahead and import the standardization package or the method from the sklearn. From sklearn dot preprocessing import standard scalar. And before I execute, or let's go ahead and execute, it doesn't have an impact, but what I wanted to say is, one of the assumptions that it takes is that your data should be normally distributed, or it should follow the Gaussian distribution. Even though it doesn't follow, you can still apply and check for the result, but idea is that it follows. And things like natural data, for example, there is a data set, temperatures data set, or the heights data set, things which fluctuates in a proper order, that means with like a nature, then you can apply those this standard scalar on that. It will work very good in that case. So if you have data which is related to the nature, follows the Gaussian distribution, this will work like a charm. All right, so let's go ahead and apply this. Std underscore scalar is equals to standard scalar, and here we don't need to specify any range or anything, and std underscore scalar equals to standard scalar dot fit, and I think that was birth underscore something. What was that? Birth array, birth, birth arr, birth underscore arr. If we execute this, so yeah, no error, no warning, so we are good. And now it would have fetched the scalar dot some parameters like mean, because it needs mean to calculate it. Standard deviation should be there. We have mean, we have std with standard deviation, so it's going to follow this. So if we say mean is this, std underscore scalar dot, there is this variance, so that is 53. Okay, so let's go ahead and try to apply it on the data. std underscore birth standard birth data equals to std underscore scalar dot transform and then birth array. So now if you see std underscore birth 0, this is what your array value looks like. std underscore birth next number 5, this is how your value look like. And you can use a for loop like this, like I mentioned earlier. If I go ever back to there, yeah, for I range 5 print birth normalize. Similarly, same method you will apply it over here to print the data, but this is also how you can go ahead and access it. So now what I'll do is I will just create the standard underscore birth underscore train and standard underscore birth underscore test data, and that is 0 to, if I am not wrong, that was 360, oh 330. Okay, 330 equals to 330 365. all right, oops, I need to specify birth underscore std standard underscore birth, std underscore birth. All right, and we can have std underscore birth underscore ARIMA equals to ARIMA and std underscore birth underscore train, and then specify the order. Everything is same, it's just this particular line, this line and this, just the standard scalar has changed. And just with this, you know, it may give us the better results or may not, if it does not follow the assumption, which I for sure know that our data does not follow any normal standard distribution. It's a very high variance data. So standard birth ARIMA, and the order that we have is, if I'm not wrong, 213 212. 212. Okay, let's see this. So this I have already explained how you will identify in the previous video, so if you have not seen, I highly recommend that, because repeating that will be something a lot of time, because that itself is a 1 hour long video. All right, so now we have the standard birth ARIMA model executed on this, and now we can do the forecast. So std underscore birth underscore forecast, no, we need to fit it, sorry about that. Birth underscore ARIMA equals to standard underscore birth underscore ARIMA dot fit, and maybe we can just change this also to this. So this is now fit, and we can see the AIC value, which is archaic information criteria, and in this case it is 918, very high. So let's go ahead and see what is going on here. std underscore birth underscore ARIMA std underscore birth underscore forecast. Let's forecast the value. std underscore birth underscore ARIMA dot fit dot forecast steps is equals to 35, and we just want the first column. So standard underscore birth underscore forecast is our value. This bit of a variation, but from when I look at this transformed data and std underscore birth underscore test, this is how the value looks like. 1.22, 0.54, 0.27, so there is a bit of a variation, and here it looks like much more consistent. So I think that this technique is not working well with the time series, but as you know, we can always evaluate by inversing it and checking the standard error of mean. So to do that, we can follow the same technique that we have done earlier. So if you have seen this, first we need to reshape, right? And then we can reverse the value of birth forecast. Okay, so birth forecast reshape is something what we need. So we will just come over here and this is basically standard birth forecast, standard std underscore birth underscore forecast, std underscore birth underscore forecast, std underscore birth underscore forecast. So now we have the reshape value. So after that, standard underscore birth underscore forecast underscore rev, that means reverse, is our scalar. I think std underscore scalar that we gave, std underscore scalar, yeah, std underscore scalar. It has the method inverse transform where we can pass on birth underscore forecast reshape. So now our this value is in proper order, and we already have birth underscore test, if I am not wrong, yeah, but this is also not properly transformed. So birth underscore test, we can transform that as well by doing the birth underscore test underscore rev equals to this is std underscore scalar and standard scalar. We need to pass. So first we need to reshape. First let's look at, this is our data, standard birth test, right? So over here, first of all, birth underscore test underscore reshape equals to same method, this particular one, birth dot reshape len comma 1. You see, pretty much the same method for reshaping it. And then birth underscore test underscore inverse or rev reverse, just to make it consistent, std underscore scalar, and within that we need to pass, we need to dot inverse transform birth underscore test underscore reshape. So now our value should be like this, right? And now we can specify the mean square error. So np dot sqrt, this to take the square root, and we need to specify the mean squared error, and within that, this first of all the actual value, which is birth test reverse, birth test rev, and then birth underscore forecast reverse, and we get the error of 7.23. So we have 7.23 here. If we see 7.23 here, almost same output if you see. So this basically indicates that both the techniques are not useful when it comes to the actual output, which is 6.86. But the main thing which I wanted to show you is how you can go ahead and apply this, because as you know, this involves a lot of data massaging, data transformation, then reshaping the data, inversing our data, all of these different techniques. And generally what happens is, this is something you need to write just once by creating a function. So what you need to do is you just create one function, let's say one for standardizing the data, one for normalizing the data, and pass on this entire algorithm that we have just seen, and within just 1 second it will give you the output. So don't think that you have to write all of this entire code again and again. It's just that you need to see how you can create the function which basically do the main operations which we have done and give you the direct output, which is over here 7.23. So there are like this normalization and standardization. There are many others like log standardization and couple of more, which I will share with you in the next couple of project videos. But this is what I had in this video for you for normalization, standardization, how you can do that. So I will upload all of this on the Google Drive, and if you want, you can get an access, or you can follow along here, as well as take the data set from there itself. And let me know if you find any problem anywhere, anything that you find it difficult to understand. And some of the things I have mentioned in my basic tutorial video which I uploaded earlier in part 1 and 2, which is a normal Python video. I highly recommend that you see that if you face problem with these operations like specifying the index or specifying the reshape and all of these things, because that's what I have explained it over there, how you can really do all of these transformation and use it in the algorithm. So I highly recommend that you see that, and let me know what your feedback is and what your comments are, as well as what you would really like to learn more in the future and want to see more from me to improve your learning. So that's about it, and I will meet you in the new video, the new topic.